Okay, let's begin. Since the rest are still coming in, let's start.
As we have already mentioned, ADC come in 0.5 volts LSB and 1 volt LSB error type. For 0.5 volts LSB type, the sample value will be coded to the nearer values in that interval. For 1 volt LSB type, the sample value will be coded to the lower values in the interval. In summary, sample rates determines the X resolution, whereas number of bits determine the number of interval on the y-axis and therefore the y resolution. Here 2 to the power of n is referring to the total number of digital level. VLSB refers to the step size of each interval.
Okay, this page give a quick summary of what we did last week. We went through 0.5 volt quantization error, maximum error type ADC, and 1 volt VLSB type ADC. And this basically, these two type of ADC, the difference is for the 0.5 volt, it will resolve the error to the nearer of the either the higher or the lower level. So if it's nearer to the higher level, it will resolve to that. If it's nearer to the lower level, it will resolve to that. But for the one VLSB type, it will be just resolving down. There's no resolving up. So it's always resolving to the lower level. Then we say that if we increase the sampling frequency, then you have more and more sample on x-axis. So therefore, it determines the x resolution. With more and more sample points, your x resolution will increase, right? Then for the y resolution is controlled by the number of bits. If you have more bits, then you have more levels, and more levels means that your steps become smaller and smaller, and therefore the y resolution will increase. And we know that for, let's say, a 3-bit ADC, 2 to the power of 3, you give you 8 levels. So this is they call it the resolution or the level. Resolution of ADC is 2 to the power of n. So this guy, if the case of 3, it will be 8 levels. So the resolution will be 8, right? Now, of course, the VLSB will be given by your V full scale. As we know, is the V full scale voltage divided by the number of interval. And interval is just basically 2n minus 1, right? Because there's less by 1 level. If there's number of level is 8, then the interval will be 7. So therefore, it's 2n minus 1. So this is quite straightforward. And of course, for an analog input, we did sample because we want to reduce the memory involved, and therefore we took samples, right? And then of course we follow the Nyquist-Shannon theorem, right? But of course, when we sample, we create a image spectrum, which may result in aliasing if we are not careful. That means we don't sample enough frequency. The frequency is not high enough. So therefore, we have to follow quite strictly the Nyquist-Shannon theorem. And then, of course, for the whole, we basically let the circuitry have enough time to do the conversion from the analog level to the respective digital level, right? And then, of course, quantization is the changing of this conversion of this analog level to the digital representation. Okay, so that is for ADC.
Next we move to the digital to analog DAC conversion. Even though the computation of the data by the microcontroller is digital, the physical environment is very much analog in nature. Hence, moving from PC back to real environment, we still need to convert it back to analog signal. DAC basically takes in digital signal and give an analog output.
So basically for this page, this slide, we are talking about, we have actually completed the signal conditioning, and we know that signal conditioning, we talk about, if the signal is noisy, then we filter it, right? Using the low pass filter, high pass filter, or band pass filter, depending on where the noise exists, right? And then if the signal is weak, we do amplification. That is the signal conditioning. Then we say that, hey, we need a translator because moving from analog to digital, we need to convert it from analog domain to digital domain. And basically, we took the 2 steps of sample and hold, and then quantization, right? Now, moving back from the controller back to the analog world, we again need another translator, right? Basically, a digital to analog translator or digital to analog conversion. That's why we call it DAC, DAC, right? So this DAC basically take in digital value and analog value. Some people tell me that, since you have analog input and digital output, then you just flip the input and output, then you become digital to analog. So it's the same. So it doesn't work this way. So we will now go through basically how to move from digital back to analog.
With digital input, microcontroller will go to a lookup table to search for the analog equivalent values.
So as we know, last week we end by saying that the digital input will be coded in a string, right? Obviously, when you want to move back from digital to analog, the computer got to decipher each of these string, each of these 3 bits code, right? So imagine that you have a 3-bit codes lying there, and let's say these are your coded signal, right, with a binary level. Now, so for digital to analog conversion, first step, they can take this 3-bit, go up to the lookup table and look for the respective voltage. So for example, I have 0, 1, 0. Look at 0, 1, 0. I will look at basically a 0.258 volt. So I will replace this 0, 1, 0 with a 0.285 volt. So this same level will be replaced by 285 volt. So respectively for all the level. So once you convert that, it will look like the picture.
This values will be the analog value for the decoded analog signal. A decoded analog signal is still pretty much staircase-like.
So if you replace each of these digital bits by its analog equivalent, then you get this value, right? But this value is still not the sine wave, still quite far from a sine wave because the edges are still jagged and square in nature, right? So what you can do is there's another step that follows.
To smoothen the effects, we use low-pass filter to filter away the higher frequency odd harmonics. The orange filtered signal is closer to the blue original signal than the gray decoded staircase signal.
Okay, I'm going to explain this further by showing you some slides. Using the whiteboard. So basically, as we know, in your basically we are trying to convert the staircase signal, right? These are your staircase signal. So these are pretty much square wave, or rather sharp edges. And these sharp edges represent that there is a lot more frequency. Just why I say so. Let's say, for example, a square wave is, if you do a Fourier transform, is actually make up of what? Is actually make up of your fundamental frequency, which is F0, right? This is your F0, plus by your third harmonics, right? So this is 3F0. So this is 3F0, plus by your 5th harmonic, which is even faster, 3F0, etc., so on and so forth, 5F0. So if you look at the frequency domain, it's basically look like that. With your fundamental being the strongest, is F0. Then you have your 3F0 that's coming in quite strong, but slightly so. Then you have a 5F0 and your 7F0, so on and so forth. You're getting smaller and smaller and smaller, right? So therefore, your square wave essentially is make up of your fundamental frequency F0 here, right? F0 here, and the rest of the harmonics, right? Now, so if you were to want to recover this fundamental frequency, which is a sine wave, all you need to do is just to put a low pass filter here and suppress all the high harmonics frequency. So all this will be shunned away, will be suppressed away, right? So what you are left with is your single frequency harmonics. So if you do a low pass filter, as a result, you will get a sine wave, which is your F0, right? So low pass filter is essentially the way to go to filter away all the edges, because all the edges are made up of high harmonics frequency that if you add up, it will become sharp edges here. Okay, clear so far? So if I were to erase this guy, you want to take a picture first before I erase? You want to snap a picture first? Can? Can I erase this part because I don't have enough space to write. So essentially, if I were to do a low pass filter here, I would expect to get pretty much the same, right? But how to do a low pass filter? Let's look at low pass filter. Low pass filter is basically consists of R and C, right? R and C, right? For a passive low pass filter, of course, there's many types of low pass filter. Let's look at a simple one, a passive low pass filter, which a V out here and a V in here. And then we know that the low pass filter characteristic of V out over V in will be equals to something like 1 over 1 plus SRC, I think. Oh, so basically, essentially, you have built a low pass filter that has a characteristic that looks this way. That has a characteristic that look at 0 dB, and of course you have at minus 3 dB, which is your cutoff frequency. This is minus 3 dB. This point here is what we call the F cutoff, your cutoff frequency. Or for this case, it will be 1 over 2 pi RC. Or for this case, it will be 1 over 2 pi RC. So this is your cutoff frequency for your filter. So you can see that, so this is how a simple RC filter can be built, right? But of course, if I were to put this to, let's say, very small resistance, so essentially this is like a short, right? This is like a short, and then I have a capacitor. So this is a special case of a RC. So of course your V in will be equals to V out, because your R is essentially 0. Then therefore, this is also acting as a low pass filter, but because the R is not there, so your frequency will change, right? Because your R originally your R is bigger, so therefore your frequency is lower, so your cutoff is lower. So if you make this to lesser value, then basically your F naught will change to higher level. So I'm looking at a higher level F naught. Why? Because I want to explain to you how a capacitor can be also used as a low pass filter. So let's take, for example, a staircase signal, a step signal. We know in a lab, we basically, if we put a capacitor through a step, basically you will charge up, right? You will charge up. Given enough time, you will charge up to the final value. And that's the RC effect of the capacitor, where tau is equals to 1 over RC or something like that, right? So you have a charging effect, right? So if I were to put this same situation to a C there, then basically your C will charge, right? Your C will charge up here. Given enough time, that will charge up here. You charge up here, then you discharge here. You discharge here. You discharge here. So you can see, so there's a charging and discharging here. So if you go back to the previous page, essentially this particular red color one, it will be talking about the C charging and discharging. So this is to illustrate to you that even without a resistor, a simple C charging and discharging, you can see that the net result is that the actual result that we want to get is to get to the blue line, right? But the staircase signal, of course, is a lot more error than as compared to your RC filter, right? Because the C filter actually has less error compared to your staircase signal. So essentially, the filter is a way to go. So if you filter, you put enough R, then the cutoff frequency move nearer to cut away more harmonics, then essentially you will get a smooth signal. Follow me so far? Clear? Clear? Huh? Okay, so shall we move to the next page? Or you want to copy the what? You want to copy the screen? Just now this screen, you want to copy it? Okay, you can snapshot this so that at least you get an idea of what I'm saying, or you can recap. Oh, okay, now I go back to the. You're done? Done, right? Done copying, or you can snapshot the screen. Okay, can I move? Can I move on to the next page?
Yeah, can.
Yeah. So I where's my share screen? Oh, blocked by this guy. So I share. Okay, so basically this page, everybody clear? So how a RC filter can actually affect the smoothing of the staircase signal.
Here is an example of a physical implementation of DAC without using lookup table. Digital input goes to S0, S1 and S2, determining whether the switch connects on disconnect to the current source above. When the switches connect, a current I, 2I, 4I etc. will flow into R depending on whether is a lower significant or higher significant bits. Each time we move up by one significant bit, the current is doubled. If you derived and write the mathematical equation, V out can finally be derived.
Any one of you after listening to this pitch can understand fully what this pitch is all about so that I don't have to explain? Can, or you all need me to go through? Can you all acknowledge? Clear? This pitch, is it clear, or you all need me to go through it?
Go through.
Go through, huh? Okay, let's go through. I can clear this screen, huh? So I clear all drawing. Now, essentially what that pitch is trying to say is, other than a lookup table, just now we saw the lookup table way and a filter, you can also use a mechanical way of generating the DAC, digital to analog converter. So if, let's say I have a DAC which composed of, let's say, I coming down, and I have 2I coming down, and I have 4I coming down, right, into three switch. So this three switch, I call it what? Let's say I call it S0, S1, S2. This is essentially your D0, D1, D2, the digital bits. And then I combine them at this point, at this point here, I combine them and I put it onto a resistor R to ground. If I put it on a resistor R to ground, then I call this point voltage here V out. Right? So this is essentially my DAC, right? My DAC. Basically, okay, let's recall what a digital bit is all about. So therefore, if let's say I have, let me change my color a bit. Let's say I have S0, S1, S2, right? So this is my digital bit. So with 3 bits, there should be 8 levels. So 8 level will be 0, 1, 0, 1, 0, 1, and 1, 2, 3, 4, 0, 1. Right? Then of course the other one will be 0, 0, 1, 1, 0, 0, and 1, 1, right? And of course the other one will be 0, 0, 0, 0, and 1, 1, 1, 1. So with that, 2 to the power of 3 will give you 8 possible level, right? 8 possible level, and these are the 8 possible level, right? So we know that for each of these level, it will give you some analog value, right? So maybe this is 0 volt, and this is your maximum, right? Maximum voltage, which is I don't know what value, right? Maximum value, right? And we know that for each of these, where's my eraser? And we know that for each of these value, if you look at it, this is like a cyclical. So for the least significant bit, it will go 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, right? So it's the most cyclical. So this represents something like your second hand, your minute hand, and your hour hand, right? For your clock. So the subsequent one will be, after the first one go by one cycle, it change states, right? And it go by one more cycle, it change states again. So it depends on the lower one going one cycle, then it change states, right? And so on and so forth. This guy also wait for the lower significant to go one cycle, then it change states, right? So it's again like same like the second hand, minute hand. Second hand has to go through 60 minutes will make 1 second. Every 60 minutes make 60 seconds make 1 minute, and every 60 minutes make 1 hour. So the hand will need to move 1 cycle in order for the minute to advance by 1. Likewise, for the minute to advance by 60 minutes, for the hour to advance by 1, right? So that's the what we call a cyclical. So it push up individually. So one cycle of this, let's say I represent this by a weightage of I, which is the case here. I represent it by a weightage of I. Then this guy, I represent it by a weightage of 2I, which is the case of this guy here, right? This guy and this guy. And this case is 4I. 4I over here. Right? So let's look at if let's say I would, of course, this digital switch will means that this guy here. So 0, 0, 0 means I open all of them. So when I open all of them, there's no current flowing down. What will be your I times R? I is 0 times R will be 0 volt, right? Quite straightforward, right? It's 0 volt. So what about 0, 0, 1? 0, 0, 1. 0, 0, 1 means that I flow down. So your output voltage here will be IR, right? Correct? Agree? Huh? Now how about 0, 1, 0? It means that the second one is closed, the other two is open. You get 2R, right? Then the third one will be 0, 1, 1. 0, 1, 1 means 1, 1 here, this one is open. So you got 3R. 2 plus 1, you get 3R. And there's this 4R. 1, 0, 0 is 1. This is a 4R. The other two open. So this one, if it is 1, 0, 1, 1, 0, 1 means that is 4R plus RI is 5I. Sorry, it should be I, not R. Sorry. 5IR. Sorry. Where's my I? There's IR. There's IR. IR. So, okay. So then if this guy, this 2, 1, the other one 0 is really 4 plus 2 is 6IR. So this is 6IR. And this is 7IR. So you can see that for each of these steps here, this is like our VLSB. VLSB is equals to IR. Oh, that means the least significant bit changes. So you take each one of them, the VLSB is the same. It's IR. Follow me? So therefore, this make up your 8-level kind of LSB. By switching this to different voltage, your V out or V out here will change, right? So essentially, what is V out? V out will be equals to your I in. This is I in, right? I in will be equals to I in multiplied by your R, right? Simple as that, right? Now, what is I in? I in is actually equals to the S0 I, S0 times by I plus by S1 times by 2I plus by S2 times by 4I. And whole thing multiplied by R. Now, S1, S2, and S0 can be 0 or 1. So if it's 0, then it's omitted, right? And it's 1, and then you calculate in. Now, how do I take out the common factor? I can take out the common factor as IR, right? Here. and then I have S0 plus 2S1 plus 4S2. Agree now? So this is what I can take it out for. Then again, if I were to say that this is also equals to 2 to the power of 0 S0 plus by 2 to the power of 1 S1 plus 2 to the power of 2 S2. Agree? Agree now? Now this is a 3-bit, n equals to 3-bit, right? N equals to 3. So therefore, this is actually n minus 1, right? So you have IR, this is n minus 2 to the power of n minus n S0 plus by 2 to the power of n minus, this is n minus 1, n minus 2, right? S1 plus by 2 to the power of n minus 1 S2. Correct? So if I take out 2 to the power of n, IR, then essentially I get what? This is s to the power of 0, so it's actually S0 over 2n plus by, of course, you get, you hold on, then you get S1 over n minus 1, right? Because 2n minus by n, it will be, so this will be 2n minus 2 S1 divided by 2n plus by 2n minus 1 over 2n S2, right? So what you get essentially? Eventually you will get something like, okay, if you work out finally, I'm not going to work out in total. Let's go to the next page to show you that essentially you will get something like that, right? I to n, you get something like that. Okay, so this is essentially able to work out to be this way. You all want to take a picture of that first? Take a picture of this so that you won't miss my explanation on this. Can? Can? Hello? Are you all done? Can someone answer me?
Can.
Okay, so now I move
can.
back. So I move back to the previous page. So this is basically that. So if you look at it carefully.
Note that the equation that is given here will be provided in the formula sheet. This V-out equation is similar to the equation derived in previous page. With that we complete chapter 3.
So you notice that this form of equation is actually the same form as the one that we just derived, right? So of course this part, it may be equivalent to your 2 to the power of n ri, right? So but of course in some of the question the v reference will be given directly. But each of these means that from your least significant bit to the most significant bit, to the power of 0 to S0 to S8 or S whatever bits you have, right? And then it will be respectively this kind of equation. So so digital to analog conversion, if you have your digital bits given and your digital pattern, let's say is 1011, you just fill up 1011 here, and you divide according to your 2 to the power of n and multiply by v reference, you will get your v out. Simple and straightforward. So essentially, what we have touched here is moving from digital to analog. You got a decoder and a filter to get your analog output. Okay, Ken? So
Please go through the tutorial 6.
Any question? So we basically finish our chapter 3. Chapter 3 on basically we have covered a few weeks, right, on chapter 3. Then we will go through the tutorial question. Then after tutorial question, we will also finish the tutorial question, and next week we will be going through the chapter 4. Ken, let's start with the tutorial question. Tutorial question is question. Where is my tutorial question? Wait, I stopped sharing this. Let me find my tutorial question first. Okay, the tutorial question is question what? The first question is question 5, right? Question 5. Let me see where is question 5. Now, question 5. I see. It says that an ADC has a resolution of 8-bit and a sampling frequency of 8,000 samples per second. So if a 3 minutes recording of a signal is made, how many samples are there? So let's go to a blank sheet. Can I clear this? Can I?
Can.
Yes.
Okay, so we talk about question 5, right? Question 5A. Question 5A. It says that the number of bits is 8-bit, right? N is 8. And it is an ADC. And it has a sample rate of 8,000 sample per second. Now the recording time is 3 minutes, right? So they ask you after 3 minutes, what is the sample size? So 3 minutes is equivalent to how many seconds? 3 times 60, right? So it's equivalent to 180 seconds. So 180 seconds will result in how many samples? Now we are using sampling frequency of this. This is fs, right? So it already tell you that in 1 second, I will generate 8,000 samples. Therefore, in 3 minutes or 180 seconds, we will therefore generate 160 seconds times by 8,000 sample per second. So total number of sample after you multiply will be 1.44 mega sample per second. Sample per second. So this is your part A. Okay, clear? Ken? Question? No, we move to part B. Let's move to part B. I go back to the question, part B. Now, write down the quantization step size of the ADC if the V full scale is 5 volt and what is the maximum quantization error? So right now they say that let's go back to the screen. And let me move this up. Now part B, it says that your reference voltage is 5 volt, right? Part B, it says that Vref, this one no, equals to 5 volt, right? Correct. And sorry, V full scale, not Vref. Is a V full scale equals to 5 volt. right? So this is a 8-bit ADC, 8-bit, V full scale is 5 volts. So what is your VLSB? Remember, your VLSB is actually what? V full scale. This is your V full scale, right? Divided by number of interval, right? What's number of interval? Number of interval is is 2 to the power of n minus 1, right? So therefore, the VLSB SB must be equals to V full scale divided by 2 n to the power of minus 1, right? So this case, your V full scale is given as 5 volt. Your bit is 2 to the power of 8 minus by 1. So it's actually what? 5 divided by 255, right? 2 to the power of 8 is 255, right? So what do you get? 5 divided by 255, you get about 19.6 millivolt. Now wait a minute. They want a maximum error, right? Sorry, the maximum error. So let's look at the question again. Now they want to find the maximum quantization error if it is a half LSB, half VLSB. Now we already found the VLSB. So what is half VLSB? Half VLSB would therefore be equals to, so your maximum quantization error maximum will therefore be equals to half VLSB, which is equals to half times by 19.6 millivolt will give you a value of 9.8, right? So this is your answer for part B. Okay, you all want to screenshot first before I move to part C? Let me move up this thing so you all can have a clearer screenshot. Okay, you all can screenshot this if you like. This is your 5A and B. Done, let me know. Then I can move on.
Done.
Done, huh? So I clear the screen, huh? I clear the screen and I move on to C. Now C, he said redesign a digital recorder, specify the maximum quantization noise of the ADC should be less than 0.1% of the V full scale of the ADC. Right? Calculate the minimum number of M bit for the ADC based on half VLSB compensation. Well, looks and sounds very complicated. Let's dissect each one of them individually. So let's go to the blank page and share. Now it says that your quantization error, right? Your quantization error maximum must be less than 0.1% of the V full scale. Now, which means that it is actually 0.1 divided by 100, right? 0.1% is 0.100 times by your V full scale. Agree? Agree, yeah? Now, this is a quantization error for what kind of ADC? Is a half LSB, VLSB ADC. And we know that VLSB for ADC is given by V full scale divided by 2n minus 1. 2n minus 1 is your interval. This is your VLSB, right? But the maximum quantization error for half VLSB is 0.5 of that, right? So you have to 0.5 multiply by this whole thing. Sorry, let me erase this part, not so clear. And I put back here. This should be 0.5. Okay, so it's 0.5. This particular thing here is VLSB, right? So essentially it is equivalent to V full scale divided by 2 times by 2n minus 1, right? Less than 0.1 over 100 times by V full scale. Now, how many unknowns are there in this equation? There's one unknown, which is V full scale, one of them, right? V full scale also here, so it is the same unknown. And then one unknown is your n, right? But the good thing is, since V full scale occur at both sides, we can cancel that, right? So that leave us one unknown, one equation. So we can solve this, right? One unknown, one equation. So if I were to rewrite it clearly, it becomes 2n minus 1, and then less than or less than equals to, okay, can? Now, if I were to reshuffle this, I move this up and move this down, right? So this will be, if I move the 100 over here, it will be 100 divided by 2, but this n plus 1, I want to move to the other side. So it's 2n minus 1, right? And then, of course, my 0.1, I move down, it will become this way, right? So this is 2 divided by 100 divided by 2, you get 50. 50 divided by 0.1, you got 500. Right? 2n minus 1. So if you move this guy over here, this is become 501 less than 2n. Oh, so if I were to do it up here, then I can take a log of both sides. Log of 501 must be less than equals to log of log of 2 to the power of n, right? This is not 2n, 2 to the power of n. So therefore, it must be equals to n times log 2 and log 501. So n must be, if I look at it this way, n must be equals to log 501 divided by log 2. So if you take a log of 501, divided by log of 2, you got a value of n must be greater than 8.969. 8.969. Of course, n can be bigger than 8.969, and it can be any number, but n must be integer, right? Because n is a bit, right? n must be integer. That's one thing, right? But let's look at the question again. I move this away and share again. Let's look at the question again. It says that calculate the minimum number. So they want a minimum n, right? So look at our solution again. We have this guy can be bigger than 8.9, but they want a minimum. So the next bigger one should be the answer, right? So therefore, it implies that the n minimum must be equals to 9. So we are looking at a 9-bit. Huh? So let's check the solution again. Right? N equals to 9. So this is the answer. Okay, I will put up the solution again. Then you all can screenshot if you like. I move this up. Okay, clear? So this is 5C, right? Is this 5C?
Yes, it is.
So I put 5C over here. Okay, you can screenshot this if you like. Okay, once you're ready, let me know. I can move on to the next question. Any questions so far for this question? Ken?
Can.
Okay, so I clear this because we are moving to the next question. Where's my share screen? Next question is question 7, right? Question 7, you can see that it is talking about control valve has a linear variation of opening as the input voltage varies from 0 to 10 volts. So this statement, what it means is, if your control voltage varies from 0 volt to 10 volt, it is going to move the control valve opening linearly, and that means in a straight line, or maybe 0 to 0%, 110 to 100%, something like that, in a straight line fashion. And a microcontroller output 8-bit. So a microcontroller output an 8-bit to control the valve using 8-bit ADC, DAC. So 8-bit the digital go in, come out analog voltage, right? To control this analog voltage will use to control your control valve. So he said, find the reference voltage required to obtain the full opening. Full opening means is at 10 volt. Full opening is 10 volt. So let's go to the workspace of the whiteboard. Let me move this guy up higher. So you have an 8 bits word, right? So 8-bit ADC DAC, right? N equals to 8, right? And your what is your, they're asking you what is your reference voltage, V reference. They're asking you what's your V reference. So what is your V reference, right? For your this deck. Now we know that basically the way this valve control operates is 0 volt to 10 volt, right? 10 volt is your full opening. This one is full close. So this is 0 to 10 volt, right? So therefore, at the full opening voltage, if one wants a full opening voltage, right? Let's see, is it they want a full opening voltage? When it is full open, required to obtain a full open valve. So therefore, they want it at a full open. So full open means that your control voltage must be at 10 volt, right? So your V out, the DAC V out is used to, the DAC has digital in, right? Your deck has digital in, digital in, and your analog out, right? Right? And this analog out is V out, right? Right? So this V out is used to control your valve. So your valve is here, is used to control your valve. So at maximum voltage, V out must be equals to 10 volt, right? At maximum voltage, that means fully open, the V out must be equals to 10 volt, right? Now we know that for the reference for the deck voltage, let me share again. Where is my previous page? Can you see this equation? This is V out equals to V ref times by a certain bits, right? So just an impression. I'm going to switch back to the screen. V out is equals to, so V out is equals to what? V out is equals to V ref multiplied by your different voltage, right? Basically your SN, S8, your S8 divided by 2 plus by your S7. Oh, sorry, this is S7 because 8 bits is S7. So S6 divided by what? S6 divided by 4, right? Plus by S5 divided by 8, right? Plus by S4, right? Divided by 16 plus by S3 divided by 32 plus by S2 divided by 64 plus by S1 divided by 128, and of course plus by S0 divided by 256, right? So that's your bits combination. Now, we know that in the maximum full opening, this must be 1, 1, 1, 1, 1, 1, 1, 1 for 8 bits, right? So all this must be 1. Agree or not? All this must be 1. So therefore, if you calculate and you put your VREF 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16 plus 1 over 32 plus 1 over 64 plus 1 over 128 plus 1 over 256. Each of these are the bits, 1, 1, 1, 1. This is S7, and this is S0, or S7 to S0. Of course, in between is the other one, S1, S2, S3, S4, S0. And then this one, we know V out is 10 volt, right? So now the question is, we've got one unknown, the rest are all known, right? So if we calculate this, this will be equals to what? This will be equals to what? This will be equals to 0.9961. So this will be equals to VREF multiplied by 0.9961. So VREF, if you calculate, will be equals to about 10.039 volt. Okay, so this is for your question question 7 part A. 7A. Ken, you want to screenshot or you? Yep, this is your 7 part A. So your VREF is basically 10.039 volt. Question? Any question so far for this? You can screenshot. Let me know when you are done. Clear so far? So can I proceed?
Yeah, can.
Okay, I clear. Now let's move to the next question. Sorry, the next part of the question. Not this one. Okay, 5B, you want to find the percentage of opening when changing one bit. Right, one bit. So let's go to the blackboard again. Now, what is one bit? Now, we know that right now, we know what is VREF, right? VREF is, sorry, V full scale is 10 volt, right? Right, V full scale is 10 volt. Because we move from 0 to 10 volt, right? And then if we want to find what is 1 V LSB, we will have V full scale divided by 2N minus 1, right? And V full scale is 10 volt, right? Divided by 2 to the power of 8 minus 1, which is 10 divided by 255. So you will get what? 10 divided by 255. Sorry, the V full scale, the V full scale should be V ref, not this V ref. So it's 10.039, right? Because that's the maximum voltage. So 10.039. Oh. So this is what we calculated just now. So 10.039 divided by 255 will give you about 39. It give you about 39.2 millivolt. Okay, so that is that. Not yet. This is not the final solution yet. They want the percentage, right? So percentage of the 1 bit. 1 bit is will cause 1 VLSB. Remember your 0000001, right? Each bits will change. This 1 bit, when they are talking about 1 bit change, is actually 1 VLSB. 1 VLSB will cause 39.2 millivolt. So this 39.2 millivolt divided by your total, right? Total will means that it is your total is ranging from 0 to 10 volt, right? So 39.2 millivolt divided by 10 will be your full scale, control voltage full scale, and multiply by 100%. This will be your percentage due to 1 bit, right? 1 bit. So therefore, this will be equal to what? 39.2 divided by 10 will give you about times 100 will give you about 0.392%. Okay. So this is your answer. For 1 bit change, it will result in 0.392% opening of the valve. Right? Clear so far? So this is your 7B. Yeah? Is it 7B? Yeah, 7B. Question 7B. So I put 7B here. Okay, you can screenshot if you like. Let me know when you are done. Okay, clear? Clear? Can I clear?
Yeah.
Clear?
Yes, please.
Okay, so now I stop sharing. So basically, today we just completed the chapter 3 and tutorial 2, right? Now tutorial 2, we may not have gone through every question. So when you guys go through it yourself and you realize, hey, you still got leave out a lot of questions. Some of the questions are pretty tough, especially those that after question 7. Question 8 and 9, I have tried sharing with students before. After that, they say brain dead, too saturated. It's even much more difficult level. And to me, I think that I will not be testing you guys at those kind of difficulty level. So therefore, I don't want to waste the time to go through it. But if you still think that you want to take the challenge, you want to go through it, by all means, you can go through it. If you got any problem, you can come to me. Okay. I will still entertain you since the question is put up there, and the solution I will also put up with those solutions. But if you look at the solution, it will be much more complicated. But the one required for this semester will be basically those that is shared so far. Can? So after this, I will post the final solution of tutorial 3 up, like the written solution. Okay, so please go ahead and try out those that has been discussed already by covering away and then doing it yourself to make sure that you really understand, and don't just take it that is very lightly, because you need to practice. Like I say, the neuroplasticity, right? I send you all the video already. Needs you to practice your brain before you cannot do a last minute work for mathematics.